Dear students, once again I welcome you all to the second semester BSc Physics class. So far we have discussed in our earlier sessions about the velocity of sound wave in air, and we have deduced expressions for the same. We have discussed about Newton's formula and Laplace's correction for the velocity of sound wave. In this session we shall discuss about expression for frequency of vibration of a stretched string and the corresponding harmonics. The vibrations can be set up in a stretched string when the string is fixed at two ends. If the disturbance is created and the disturbance travels in the stretched string from one point to the other point, and this disturbance will be get reflected and there will be some loop formation. The string starts vibrating in different modes, and those are called different harmonics. We will discuss this in our next slides. When the string vibrates, there are stationary waves formed or set up. These stationary waves are the transverse waves, which starts from one end and travels or propagates to the other end in the medium of the string, and these waves again reflected from the other end and comes back. Hence this repeats, and the waves set up in the medium of the string are being reflected from the two fixed ends. The transverse wave which travels along the string with some velocity depends on certain constants of the string. Velocity v of the transverse vibration along a string can be given by v is equal to square root of t by rho, where t is the tension in the string and rho being the density of the string respectively. According to this equation, the velocity of the transverse vibration along a string depends upon tension and density of the string. The velocity is directly proportional to the root of the tension, and it is inversely proportional to root of density of the string material. In this picture you can observe the string can vibrate in different modes of vibration. So while the transverse wave is set up in the string, the string can vibrate in different modes by forming different types of loops. In the first figure you can observe there is a formation of only one loop. This loop is formed when there is a formation of two nodes at the two fixed ends, and in between an antinode is formed. Antinode is formed where the vibration of the particle of the medium is maximum, and nodes are formed at the positions where the vibrations of the particles of the medium is minimum or zero. You can observe and compare the different types of formation of nodes and antinodes with the formation of different loops in the four figures here. In the second figure there is a formation of two loops, so where three nodes and two antinodes are formed. In the third figure, there is a formation of 3 loops in the string. It comprises of 4 nodes and 3 antinodes. And so on, we get different modes of vibration in the string. Now let us move into the deduction of an equation for the frequency of vibration in the stretched string. For this, let us consider L be the length of the string. If the entire string is split into R number of segments or R number of loops, then the length of the string is given by L is equal to R into lambda by 2. In the previous slide, you have observed that there are formation of different segments or loops. One segment is named as, it is represented by the letter R in this equation, and the wavelength corresponding to one segment or one loop is half of the wavelength of the wave propagating in the string. Therefore, one length L comprises of R times the half wavelengths in the medium, that is equal to L is equal to R into lambda by 2. With this reference, we can write the same equation can be rewritten as lambda is equal to 2L divided by R. But we know that the velocity or the speed is equal to, it is the product of frequency and wavelength. V is equal to N into lambda, where lambda is the wavelength and N is the frequency of vibration. We can write lambda is equal to V by N. So these are the two equations 2 and 3. Next, we can compare the equations 2 and 3 and we get V by N is equal to 2L by R, or this can be written as N is equal to R by 2L into V. The above equation is written in terms of the frequency of vibration, that is N represents the frequency of vibration. Now this equation 4 can be compared with the equation number 1 and we get the expression for the frequency of vibration as N is equal to R divided by 2L into square root of T by rho. Hence the string can vibrate in different modes within the length of the string. When the string vibrates within the length, we get different modes and we get a 2, 3, 4, etc. number of loops formed in the string. Now we shall look into different cases. We have assigned R as the representation of number of loop or segment formed in the string. Now let us consider R is equal to 1, that is one loop is formed. Then the frequency of the fundamental note emitted can be given by N1 is equal to 1 by 2L into square root of T by rho. So this equation we get from the substitution for R in the previous equation number 5, which is the equation or the expression for the frequency of vibration in a stretched string. Hence, if R is equal to 1, if a single loop is formed, then that frequency is known as the fundamental frequency. Now, when R is equal to 2 loops, the frequency of the first harmonic, that means if there are 2 loops are formed, this is known as the second fundamental note, or it is the first harmonic. The equation for this first harmonic can be given by N2 is equal to 2 by 2L into square root of T by rho. We can replace this in terms of the fundamental note. Therefore, N2 is equal to 2 into n1. n2 is twice n1. Next, if we consider the case when r is equal to 3 loops, the frequency of the second harmonics will be emitted. That can be given by n3 is equal to 3 divided by 2l into square root of t by rho. In each equation we are replacing r value as 1, 2, 3, etc. and getting different harmonics. So in the second harmonics, that is n3 is equal to 3 into n1. That is n3 is thrice n1, we can say. So in a similar way, if r is equal to s loops are formed, we get the frequency of the harmonic emitted by the string, and that frequency can be given by ns is equal to s divided by 2l into square root of t by rho, which is equal to s times n1. So thus different harmonics are formed in a stretched string, and these harmonics formed in a stretched string are the integral multiple of the fundamental frequency only. So here n1 represents the fundamental frequency, and the next harmonic which is formed according to the number of loops will be the integral multiple of the fundamental frequency only. It is found that the frequency gravest role or fundamental n1 is inversely proportional to the length of the vibrating string when tension and the line density remain constant, and the fundamental frequency n1 is directly proportional to the square root of the tension to which the string is subjected when the length and line density remain constant. It is also inversely proportional to the square root of the linear density of the string when the length and tension remain constant. Thus, the natural frequencies, the normal modes of oscillation of a system are obtained. As I explained earlier, the lowest possible frequency of the system is called as its fundamental mode or the first harmonic. Next, the higher frequencies which are formed are called as overtones. The first overtone is the second harmonic. Like that we can say there are overtones formed. Hence the integral multiples of the fundamental frequency are called as harmonics. When the string vibrates with one loop, the frequency of the emitted loop is n1, as in the equation number 6, is the lowest and the note is the fundamental. When it vibrates with two loops, the frequency n2 is doubled as that of the fundamental, and the corresponding note is the second harmonic, or it is also known as the first overtone, as in the equation number 7. The three loops have a frequency n3, thrice that of the fundamental, and the frequency n1 is the third harmonic or the second overtone, and so on. Hence, this is about the expression for the frequency of vibration of a stretched string and the explanation of the harmonics formed in the stretched string.